Artificial intelligence, or AI, is advancing at a remarkable pace. We see this progress everywhere around us today, in 2025. Just a few decades ago, AI was mostly confined to research laboratories. It existed in theories and in very specialized, limited applications. Now, AI systems can perform tasks that once seemed impossible for machines. They can defeat world champions in complex games like Go and chess. They can recognize faces in a crowd with surprising accuracy. They compose music and create art. This rapid development shows an exponential trend, a hallmark of information technology. The capabilities of AI are growing, and they are growing faster every year. The impact of AI is already transforming our daily lives in profound ways. Many of us carry AI in our pockets, powering the assistants on our smartphones. AI algorithms curate the news we read and suggest products we might like to buy. In healthcare, AI helps doctors diagnose diseases earlier and more accurately. It analyzes medical images to detect patterns humans might miss. In transportation, AI is the driving force behind self-driving cars, promising a future with safer roads. It optimizes logistics and supply chains. AI is not just a futuristic concept anymore, it's a present-day reality, quietly revolutionizing industry after industry across the globe. The ultimate promise of AI is truly vast. Scientists and engineers dream of creating artificial general intelligence, or AGI. This would be AI with the ability to understand or learn any intellectual task that a human being can. Such a breakthrough could help us solve some of humanity's most challenging problems. Think of climate change, disease eradication, or deep space exploration. AI could augment human intelligence, leading to an unprecedented era of discovery and innovation. This is the grand vision that fuels much of the research and development in the field. The creation of truly intelligent machines could mark a new stage in the evolution of intelligence on Earth. However, it is important to remember that AI is still on a journey of evolution. Current AI systems, while powerful, are typically narrow AI. This means they excel at specific tasks they are trained for. An AI that plays Go cannot suddenly drive a car or diagnose a medical condition without entirely new training and programming. AI learns from vast amounts of data, identifying patterns and making predictions. But the flexible, adaptable, general intelligence that humans possess is a different kind of capability. Achieving that level of understanding and consciousness in machines remains a significant and fascinating challenge for the years ahead. The human brain is truly a marvel of biological engineering. It is an organ of incredible complexity and astonishing efficiency. Billions of years of evolution have meticulously shaped it into the powerful thinking machine it is today. Weighing only about 3 pounds, it consumes a remarkably small amount of energy. Yet it is the source of all our thoughts, our emotions, our memories, and our dreams. It is the seat of our consciousness, the very essence of what makes us human. Understanding its intricate workings is one of the greatest scientific quests of our time, a challenge that fascinates and humbles us. Our brains endow us with a unique suite of capabilities. We possess creativity, allowing us to imagine new worlds and invent novel solutions. We can compose breathtaking symphonies, write poignant poetry, and design intricate works of art. We have profound emotional intelligence, enabling us to connect with others, feel empathy, and navigate complex social situations. Our capacity for abstract thought allows us to ponder philosophical questions, develop scientific theories, and understand mathematical concepts. These abilities go far beyond simple pattern recognition. They involve deep understanding and a rich internal experience of the world around us. Furthermore, the human brain exhibits remarkable adaptability and a lifelong capacity for learning. From the moment we are born, our brains begin to absorb information from the environment. We learn to walk, to talk, to read, and to understand the world through continuous interaction and experience. Unlike many current AI systems that require explicit programming for new tasks, the human brain can generalize knowledge from one domain to another. It can learn from very few examples or even from a single instance. It can also reorganize itself, forming new neural connections in response to injury or new learning, a property known as neuroplasticity. Perhaps the most profound aspect of the human brain is the mystery of consciousness. How do the physical interactions of neurons and chemicals give rise to our subjective experience of the world? What is the nature of self-awareness, the feeling of I that each of us possesses? These are deep philosophical and scientific questions that we are still striving to answer. AI can simulate intelligent behavior, but creating genuine consciousness in a machine is a far more complex endeavor. The human brain remains the only example we know of a system that can generate this rich, subjective inner life, making it an enduring enigma. To understand the brain's power, we must first look at its fundamental structure. The human brain is composed of an estimated 86 billion neurons. These are specialized cells that act as the primary information carriers. Each neuron can form thousands of connections with other neurons. These connections are called synapses, and there are trillions of them in a single brain. This vast, interconnected network is organized into larger structures. The major parts include the cerebrum, responsible for higher cognitive functions, the cerebellum, crucial for motor control and coordination, and the brainstem, which manages vital life functions like breathing and heartbeat. Each part plays a specialized role in an integrated system. The neuron itself is the basic building block of this complex organ. Neurons communicate with each other using a combination of electrical and chemical signals. When a neuron is activated, it generates an electrical impulse called an action potential. This impulse travels down the neuron's axon, a long fiber. When it reaches a synapse, it triggers the release of chemical messengers known as neurotransmitters. These neurotransmitters cross the synaptic gap and bind to receptors on the next neuron, either exciting or inhibiting its activity. This intricate dance of signals, repeated billions of times per second, forms the basis of all brain activity and thought processes. Different regions of the brain are specialized for particular functions, though they work in close concert. The frontal lobe, located at the front of the head, is critical for planning, decision-making, problem-solving, and working memory. The temporal lobes, found on the sides, are heavily involved in memory formation, hearing, and language comprehension. The occipital lobes at the back are dedicated to processing visual information from our eyes. The parietal lobes, situated near the top and back, integrate sensory information from various parts of the body, such as touch, temperature, and pain. This specialization allows for efficient processing, but complex tasks require widespread collaboration across these regions. One of the most remarkable features of the brain's architecture is its plasticity. Neuroplasticity refers to the brain's ability to reorganize itself by forming new neural connections throughout life. This allows the brain to adapt to new experiences, learn new skills, and even recover from injury to some extent. For example, when you learn a new language or a musical instrument, your brain physically changes, strengthening certain pathways and creating new ones. This dynamic quality is fundamental to learning, memory, and our ability to adapt to an ever-changing world. It makes the brain a constantly evolving, living network rather than a fixed, static machine. Cognition is the term we use to describe all the mental processes involved in thinking, knowing, remembering, judging, and problem-solving. It is an incredibly complex symphony conducted by the human brain. Every moment of our waking lives, our brains are engaged in perception, taking in sensory information from the world around us. They filter this information, pay attention to what is important, and interpret it based on past experiences and current goals. This allows us to make sense of our environment and interact with it effectively. Language processing, reasoning, and decision-making are all integral parts of this intricate cognitive performance. Information processing in the brain occurs through specific neural pathways. When sensory organs, like our eyes or ears, detect a stimulus, they convert it into electrical signals. These signals travel along nerve fibers to dedicated areas in the brain for initial processing. For instance, visual information goes to the occipital lobe, while auditory information heads to the temporal lobe. From these primary sensory areas, the information is relayed to other brain regions for further analysis, integration with other information, and ultimately the generation of a response or the formation of a memory. This flow of signals through complex, interconnected networks is what allows us to perceive and understand our world. The communication between neurons, which underpins all these cognitive processes, is critically dependent on neurotransmitters. These are chemical messengers that transmit signals across the synaptic gap, the tiny space between neurons. There are many different types of neurotransmitters, each with specific functions. For example, dopamine is involved in reward, motivation, and motor control. Serotonin plays a role in mood regulation, sleep, and appetite. Acetylcholine is important for learning and memory. The precise balance and interaction of these chemicals are crucial for normal brain function. Imbalances can lead to various neurological and psychiatric conditions, highlighting their importance in the symphony of thought. A central, enduring question in neuroscience is how these physical processes, the firing of neurons and the release of chemicals, give rise to the emergent property of consciousness. How does the objective activity of brain cells create our subjective, first-person experience of reality? This includes our awareness of ourselves, our thoughts, our feelings, and the world around us. While we can map the neural correlates of consciousness, identifying brain activity associated with conscious states, the fundamental mechanism by which consciousness arises remains one of science's deepest mysteries. It is the ultimate product of the brain's complex orchestra, a melody we are still striving to fully comprehend. Section 5. Digital Minds, AI's Quest to Replicate Neural Processes. The development of artificial intelligence has long been inspired by the human brain. Early pioneers in AI research, dating back to the mid-20th century, recognized the brain's remarkable ability to learn and adapt. They dreamt of creating machines that could mimic these human-like learning processes. The concept of an artificial neuron, a simplified mathematical model of a biological neuron, was a foundational idea. This led to the exploration of how interconnected networks of these artificial neurons could potentially learn from data and perform intelligent tasks. The brain served as the ultimate blueprint, a natural system that demonstrated the possibility of intelligence emerging from interconnected processing units. This inspiration led directly to the development of artificial neural networks, or ANNs. An AN is a computational model composed of layers of interconnected nodes, often called artificial neurons or units. These networks typically have an input layer which receives raw data, one or more hidden layers which perform computations and feature extraction, and an output layer which produces the final result or prediction. Information flows through the network, with each artificial neuron processing its inputs and passing its output to neurons in the next layer. The strength of the connections between these units, known as weights, determines how the network processes information, much like synapses in the biological brain. Learning in ANs is a process of adjusting these connection weights based on experience, which usually means training data. One common learning algorithm is called backpropagation. During training, the network is presented with examples and its output is compared to the desired output. If there is an error, the backpropagation algorithm calculates how much each weight in the network contributed to that error. It then adjusts the weights in a way that reduces the error for future predictions. This iterative process of trial and error, guided by data, allows the AN to learn to perform specific tasks, effectively mimicking the concept of synaptic plasticity seen in biological brains, where connections strengthen or weaken with experience. The field of deep learning represents a significant advancement in ANs. Deep learning models are essentially ANs with many hidden layers, hence the term deep. These additional layers allow the network to learn hierarchical representations of data. For example, in image recognition, lower layers might learn to detect simple features like edges and corners, while higher layers combine these features to recognize more complex patterns like objects or faces. Deep learning has achieved state-of-the-art results in many areas, including image recognition, natural language processing, and speech recognition. However, it's crucial to remember that even these sophisticated ANs are still highly simplified models compared to the intricate complexity of the human brain. Section 6. Cognitive contrasts, charting the differences between AI and us. When we compare artificial intelligence and human cognition, we find a fascinating landscape of both overlapping capabilities and stark differences. AI systems, particularly those based on deep learning, demonstrate remarkable strengths in specific domains. They can process and analyze vast quantities of data at speeds far exceeding human capacity. They excel at pattern recognition, identifying subtle correlations in complex datasets that might be invisible to a human observer. AI algorithms can perform repetitive tasks with unwavering accuracy and consistency, as they do not suffer from fatigue or boredom. These attributes make AI incredibly powerful tools for data-intensive applications. Humans, on the other hand, possess a different set of cognitive strengths, often characterized by breadth and flexibility. We have general intelligence, the ability to reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, and learn from experience. This is not tied to a single narrow task. We exhibit robust common sense reasoning, drawing on a vast background of implicit knowledge about how the world works. Our creativity allows for genuine novelty and innovation, not just recombination of existing patterns. Furthermore, human emotional understanding and empathy are deeply ingrained, enabling rich social interactions and nuanced communication. The way AI and humans learn also presents significant contrasts. Most current AI models require massive datasets for training. A deep learning system might need to see millions of images to learn to recognize cats with high accuracy. Humans, especially children, can often learn new concepts from just a few examples or even a single instance. We learn continuously through rich, multimodal experiences, including social interaction, exploration, and play. AI learning is typically more structured, driven by specific algorithms and objective functions defined by programmers. The human brain's learning mechanisms are far more diverse and integrated with our overall cognitive architecture. Another critical difference lies in energy efficiency. The human brain, despite its incredible computational power, operates on approximately 20 watts of power. This is comparable to a dim light bulb. In contrast, the large-scale AI models and supercomputers used to train and run them can consume megawatts of power, requiring dedicated cooling systems and substantial energy resources. This highlights the remarkable efficiency that biological evolution has achieved in designing the brain. Bridging this energy efficiency gap is a significant challenge for the future development of AI, especially as we strive to create more complex and capable artificial intelligence systems. Section 7. The frontiers of emulation, what AI awaits to learn. Despite the rapid advancements in artificial intelligence, there are significant aspects of human cognition that AI has yet to replicate successfully. One of the most profound of these is true understanding and consciousness. Current AI systems, including sophisticated language models, can process and generate human-like text. They can answer questions and even engage in seemingly coherent conversations. However, they do not possess genuine understanding of the meaning or context behind the words they manipulate. They lack subjective experience, self-awareness, and the rich inner world that characterizes human consciousness. AI mimics understanding, it does not yet possess it. Genuine creativity and intuition are other areas where human abilities still far surpass those of AI. AI can be trained to generate art, music, or text in specific styles by learning patterns from existing works. However, human creativity often involves a departure from established patterns driven by insight, inspiration, and a deep conceptual grasp of the domain. Intuition, that feeling of knowing something without conscious reasoning, is another human trait that is difficult to codify and replicate in machines. It often arises from years of experience and implicit learning, allowing us to make quick, effective judgments in complex situations. Emotional intelligence and empathy represent another significant frontier for AI. While AI systems can be programmed to recognize and simulate human emotions, for example, by analyzing facial expressions or tone of voice, they do not actually feel these emotions. True empathy involves understanding and sharing the feelings of another, a capability deeply rooted in our biological and social nature. Building AI that can not only recognize but also respond appropriately and authentically to human emotional states in a way that fosters genuine connection remains a complex challenge. This is crucial for AI systems intended to interact closely with humans in roles like companionship or care. Finally, AI systems often struggle with robust generalization and common sense reasoning, especially when faced with novel situations not covered in their training data. Humans possess a vast reservoir of common sense knowledge about the physical world, social interactions, and cause and effect relationships. This allows us to navigate unfamiliar environments and solve unexpected problems with relative ease. AI, on the other hand, can be brittle. Its performance may degrade significantly when encountering situations even slightly different from what it has learned. Imbuing AI with a human-like capacity for common sense and broad adaptability is a key area of ongoing research and a major hurdle to overcome. Section 8. Convergence, how AI and neuroscience propel each other forward. The relationship between artificial intelligence and neuroscience is increasingly becoming a two-way street, a path of convergence fostering mutual advancement. Historically, neuroscience has provided significant inspiration for AI. The very concept of artificial neural networks, as we've discussed, is drawn from the structure and function of the brain. Modern AI research continues to look to the brain for new ideas. For example, reinforcement learning algorithms, which allow AI agents to learn through trial and error by receiving rewards or punishments, are inspired by how animals and humans learn through dopamine-driven reward systems in the brain. Understanding brain mechanisms can spark novel AI architectures and learning paradigms. Conversely, AI is now providing powerful tools and frameworks that are accelerating progress in neuroscience. The brain is an incredibly complex system, generating vast amounts of data from techniques like fMRI, EEG, and single-unit recordings. AI and machine learning algorithms are proving invaluable for analyzing this complex neural data, helping neuroscientists identify patterns, decode brain activity, and build more accurate models of brain circuits. AI can simulate brain activity under various conditions, allowing researchers to test hypotheses about neural function and dysfunction that would be difficult or impossible to test in living brains. This computational approach complements traditional experimental neuroscience. One exciting area where AI and neuroscience converge is in the development of brain-computer interfaces, or BCIs. BCIs are systems that create direct communication pathways between the human brain and external devices, such as computers or prosthetic limbs. AI algorithms play a crucial role in decoding the complex neural signals recorded from the brain, translating them into commands that can control these devices. This technology holds immense promise for restoring lost sensory or motor functions in individuals with paralysis, neurological disorders, or limb loss. The synergy between understanding brain signals, that is neuroscience, and interpreting them intelligently, which is AI, is key to advancing BCI capabilities. This cross-pollination of ideas is fostering a new era of collaborative research. Large-scale projects and initiatives are increasingly bringing together neuroscientists, AI researchers, cognitive scientists, and engineers. They share data, tools, and theoretical perspectives, working towards a more unified understanding of both natural and artificial intelligence. By studying the brain, AI researchers can gain insights into building more robust, flexible, and efficient intelligence systems. By using AI to model the brain, neuroscientists can gain deeper insights into the mechanisms of cognition, perception, and consciousness. This collaborative spirit is essential for tackling the grand challenges in both fields. Section 9. The next chapter of Intelligence AI, Unveiling the Secrets of Thought. Artificial intelligence is poised to play an increasingly vital role in our quest to understand the human brain and the nature of thought itself. By attempting to build systems that can mimic aspects of human cognitive function, we are essentially creating testable models of our own minds. When an AI model successfully replicates a human-like behavior, it can provide clues about the underlying mechanisms that might be at play in the biological brain. Conversely, when an AI model fails, it highlights the gaps in our current understanding, pointing us towards areas where more research is needed. This iterative process of building, testing, and refining AI can be a powerful engine for discovery in neuroscience. The future may see the development of advanced AI systems that can simulate not just specific narrow tasks, but also more complex aspects of human thought. This could include more sophisticated forms of reasoning, problem-solving in unfamiliar domains, and perhaps even rudimentary forms of learning that more closely resemble human learning. While the creation of true artificial general intelligence or conscious AI remains a distant and highly debated prospect, even progress towards more integrated and flexible AI could revolutionize how we approach understanding intelligence. These advanced AI models could serve as digital laboratories for exploring the principles of cognition. As AI systems become more capable of mimicking and potentially one day replicating aspects of human thought, we will inevitably face profound ethical considerations, questions about the nature of consciousness, personhood, and the rights of intelligent machines will move from philosophical discussions to practical concerns. If an AI can convincingly express emotions or claim self-awareness, how should we treat it? What are the societal implications of creating entities that can think and learn in ways that approach or even surpass human capabilities? Navigating these ethical waters will require careful thought, open discussion, and a strong commitment to ensuring AI develops in a way that benefits humanity. The journey to understand our own minds and to create artificial intelligence is one of the most exciting and significant endeavors in human history. We stand at a unique point in time in 2025 where the convergence of neuroscience and AI is accelerating our progress on both fronts. The future implications are immense, potentially leading to breakthroughs in medicine, education, and our fundamental understanding of what it means to be intelligent. The quest to decipher and recreate thought is not just about building smarter machines. It is about unlocking the deepest secrets of our own existence. The horizon of understanding is vast, and the path ahead is filled with both challenges and extraordinary promise.